Welcome to Cloud Perceptor's guide on neural networks, designed specifically for beginners. Today, we'll unravel the complexities of neural networks and make them easy to understand. The human brain, with its 86 billion neurons, serves as a marvel of parallel processing. Each neuron processes information and transmits signals, forming connections known as synapses. These synapses strengthen or weaken over time, a process called synaptic plasticity, which is crucial for learning and memory. Artificial neural networks, or ANNs, are computational models inspired by the structure and function of biological neural networks. In an ANN, artificial neurons, also known as nodes, are organized into layers. The input layer receives raw data and converts it into a format that can be processed by the neural network. This layer typically consists of nodes, each representing a single feature or input variable, and connects to the first hidden layer. Hidden layers process input data through multiple layers of interconnected nodes. They are responsible for learning complex relationships between input data and output. Each hidden layer consists of nodes connected to previous and subsequent layers, allowing the network to learn intricate patterns. The output layer produces the final prediction or classification. It typically consists of a single node representing the probability of each possible outcome. The neural network makes a prediction by calculating the output of this layer. Activation functions are crucial components of ANNs, introducing non-linearity into the network. This enables the network to learn complex patterns and relationships in the data, which would be impossible with linear transformations alone. Imagine a binary classification task where we predict whether a customer will churn. The sigmoid activation function is ideal for the output layer as it squashes the output value between 0 and 1, providing a probability estimate. For hidden layers, the ReLU activation function is often preferred due to its computational efficiency and ability to mitigate the vanishing gradient problem, a common issue in deep neural networks. Perceptrons are the simplest form of ANNs, consisting of a single layer of output nodes. Each input node connects to each output node, and the connections are weighted. The perceptron calculates a weighted sum of the inputs, adds a bias term, and passes the result through an activation function. A perceptron can be trained to perform the logical and operation. Given two binary inputs, the perceptron should output 1 only if both inputs are 1. This is achieved by setting appropriate weights and bias for the perceptron. Training an ANN involves feeding it a large dataset of examples and iteratively adjusting the weights and biases to minimize the error between the predicted output and the actual output. This process, known as backpropagation, updates the weights by propagating the error backward through the network. Consider an image classification task where we identify cats and dogs in images. A convolutional neural network, CNN, can be trained on a large dataset of labeled images, learning to extract relevant features to make accurate predictions. Neural networks are a rapidly evolving field with various architectures, each with its strengths and weaknesses. Examples include recurrent neural networks for sequential data, generative adversarial networks for generating realistic data, and transformer networks for natural language processing tasks.